In this video, we're going to look at improper integrals. We'll start by defining them, and then we'll look at how to calculate them if they exist. So, an integral is improper if the integrand, which is the thing we're integrating, so here it's 1 over x squared. So, integral is improper if it's undefined at either the upper limit, the lower limit, or a value in between. So this first example here, 1 over x squared dx, the integral of 1 over x squared dx between 1 and infinity is undefined because the upper limit is infinity. So in an exam question, you'll say, or if you're asked, why is this integral improper? You'll just simply say, all right, it's improper because the upper limit is infinity. For exactly the same reason, the last one here is also improper because the upper limit is infinity. And when I say undefined, well, 1 over infinity squared, you could say that's infinite, something that's very, very small, but it's not equal to a number. We can't actually work out 1 divided by infinity squared. Okay, so because infinity itself is not a number. So this is undefined because the upper limit is infinity. It's improper because the upper limit is infinity. This is improper because my lower limit, because my integrand is undefined at my lower limit. I can work out 1 over the square root of 1. That's not a problem. But 1 over the square root of 0 is undefined. I can't do 1 divided by 0. So this one is improper because my integrand is undefined at my lower limit, which is 0. Or you can write anything that says something like that. You can just say improper because my lower limit is 0, or improper because 1 over the root of x is undefined at 0. Now this one, we've already seen the last one, so this one's just improper for exactly the same reason as the first one is. This one is improper not because of my upper or lower limit. I can work out 1 over 1 squared. I can also work out 1 over minus 1 squared. It's 1 in both cases. But in between minus 1 and 1, I have the number 0. And 1 over x squared is undefined at 0. So I've got my 3 conditions for something to be improper. It's either undefined at my upper or lower limit, so it could be infinity, or it could be just something that makes you divide by 0, or some value in between. So this one you say is improper because 1 over x squared is undefined at 0, which is in between my upper and lower limit. Okay, so let's look at a few examples. Let's look at before we look at some examples, remember an integral is essentially just working out the area underneath the graph. So these are the 4 graphs associated with those 4 integrals we've just seen. This is the integral between 1. So integral of 1 over x squared, so this is the 1 over x squared graph. And this is the area underneath this graph for x values going from 1 to infinity. For 0 to 1 here, for minus 1 to 1 here, and for 0 to infinity here. Well, clearly this one, we can say, isn't actually equal to some value. Well, this is getting infinitely big. This is not equal. It's not going to be equal to some number. Well, the other 3, well, they may or may not be equal to a number. So that's what we're going to work out. And we're going to look at how we work that out. So let's look at first example. So we're going to work out, the integral of these 2 integrals. So let's do the first one. So when doing this, so I'll start off up here. So we're going to work out the integral between 1 and infinity of 1 over x squared dx. And we can't do this. The problem is this infinity. So we're going to replace that infinity with a letter. Now it could be any letter. Well, don't use x, but any other letter, x or y really shouldn't use. But usually we use letters a or b. So, and don't use c because we use that as the constant of integration. So I'm going to replace that infinity with an a. The 1 is not a problem, so that's going to stay a 1. We're still working out the integral from 1 over x squared dx. Now these 2 aren't equal yet. I can't just replace an infinity with an a. What we can do, though, this will be equal if I say this is equal to this as a tends to infinity. Now this isn't a problem now. This thing I can actually work out. It's a definite integral. A is just some number. You just work. All you need to do now, so the rest of the process is work out this definite integral and then just work and then find what that tends to as a tends to infinity. Okay, so we're going to do that now. So I'm going to keep on writing the limit bit, but we're not going to do anything with the limit until the end. So limit as a tends to infinity. We're going to work out this integral. So if I integrate 1 over x squared, that is, well, remember this is x to the power minus 2, raise the power by 1, divided by the power. So this is a simple C1, C2 integration. So it goes to x to the power minus 1 over minus 1, but x to the power minus 1 is 1 over x. So this whole thing is just simply, this integral is simply minus 1 over x. And it's definite, so we need to work out between the values of 1 and a. So let's plug those in now. So when I plug in a into here, so still limit, but again, notice I'm just working out the definite integral, not doing anything with the limit just yet. So plug in a in here, of course, we'll get minus 1 over a. Technically, I should probably put brackets around this. Again, I should have probably put brackets around it. It doesn't really matter. So limit as a tends to infinity of minus 1 over a. Plug in 1 into here. So we get minus 1, but it's minus 1. Remember, when we're doing definite integral, we plug this in and then take away what we have when we plug this in. When we plug this in here, we get -1. Now what is this? Now we finally work out the limit. So as a tends to infinity, this thing here, think about this as a gets infinitely big. What is 1 divided by something that's infinitely big? Well, it's going to go to 0. As a tends to infinity, this tends to 0. So this whole thing, so 0 minus -1, so it's just +1. That's it. So this integral that we looked at of 1 over x squared between 1 and infinity is equal to 1. So this area, if you go back to the graphs, this area has size 1. Okay, so let's look at the second example here. Example 2, we work out the integral between 0 and infinity of root x dx. So this is the same kind of problem we have in the first one. We have an infinity at the top, so we're going to do exactly the same thing as we did. We're still going to use it as a limit. So try this on your own, actually. Although this one's slightly different from the other one when we get to the last bit. So, but most of it is the same. So limit as a tends to infinity of the integral of 1 to a of root x dx. Sorry, I should have written a dx here. Now, of course, this is x to the power half. Raise x to the power half goes to x to the power 3 over 2. Again, limit as a tends to infinity is x to the power 3 over 2 over 3 over 2. Divided by 3 over 2 is the same as timesing by 2 over 3. And we're working this out between 1 and a. So that's equal to limit as a tends to infinity. Well, plug this in here. So it's 2a to the power 3 over 2 over 3 minus, sorry, there should be a 0. Okay, I made a mistake here because previously it was 1. So I just kept on writing 1 here. So it was between 0 and infinity. So it's between 0 and a. It's between 0 and a here. Okay, a still tends to infinity because I replaced this a replaces that infinity, so a tends to infinity. That bit's fine between 0 and infinity. So do check this. Okay, so of course when I plug in 0 into this, I get nothing. So this integral is simply equal. So this is just simply equal to. So this is simply equal to. So of course, get rid of this minus because we don't need it. Now let's work this out. Or is this equal to anything? Well, as a tends to infinity, well, let's look at this. We've got a to the power 3 over 2. Well, a to the power 3 over 2 is a square root of a cubed. It's bigger than a. So as a gets infinitely big, so does this. Now, the fact that we multiply by 2 and divide by 3 doesn't really matter, because a is getting infinitely big. So dividing something that's infinitely big by 3 is still something infinitely big. So this doesn't actually go to any value. So, but be careful, we don't write equals to infinity. Right? Don't write equals infinity. So what we're going to write here, we're going to put arrow tends to infinity because this gets infinitely big. So does this limit actually exist? It doesn't. Don't write your answer isn't infinity. So what you should say is this. So this integral doesn't exist. So this integral doesn't exist or is undefined. So you say it doesn't exist. The first one did exist and it had a value of 1. This one doesn't exist. Notice I don't write equal. You can't. It's not equal to 1. This thing tends to infinity. Okay. A couple more examples. We want to work out the integral between 0 and 1 of 1 over root x. By the way, actually, let's look at this one. So this one graphically, it is what we confirmed what we said earlier. The graph, this is this, and this gets infinitely big. So area under the graph, or the integral between 0 and 1 over 1 over root x. And do everything exactly the same as we did before. So let's just write down the question. So dx, and of course, so now we replace. So we're working out the limit. And now what the problem this time is, it's not the 1. It's not my upper limit. My problem in this case is my lower limit of 0 because I can't work this out at 0. So I replaced the 0 with an a. Still 1 at the top. So now it's the limit as a. Now a is replacing a 0. So it's not a as a tends to infinity. It's as a tends to 0. I still 1 over root x dx. Now let's work out this integral. So now we're just going to work out this definite integral. Ignore the limits. We're going to keep on writing it, but we don't. So this is x to the power minus a half. Because x to the power half, 1 over is 1 over x to the power half. So x to the power minus a half. Raise the power by 1 divided by the power. So x goes to x to the power minus a half goes to x to the power 3. X to the power of a half divided by a half. So x to the power half divided by a half is 2 to x to the power half. I'm going to write it as a 2 root x. Is in between a and 1, and it's still limit we still have the limit as a tends to 0. But again, like before, we're not going to do anything with that just yet. So limit as a tends to 0. Let's work out this definite interest, plug it in. So it's 2 root 1. So again, we're not doing anything with this limit. So really, I should probably put a bracket around this whole thing. Doesn't, I mean, from context, it makes sense what we're doing anyway. So 2 root 1 is just 2 minus 2 root a. So it's 2 minus 2 root a. Now let's work out this limit. Well, as a tends to 0, well, first of all, this 2 is unaffected. There's no a here. And this bit, well, as a gets smaller and goes to 0, so does root a. So this goes to 2 times 0. So this is just 0. So this is just equal to 2. So this integral is equal to 2. And let's go back to our graph, what this means. So I think the one we just did was this one. So this area here has a value of 2. Okay, and finally, we've got one left, which is this integral of 1 over x squared between minus 1 and 1. Now, the problem with this one, as I said before, isn't the upper or lower limit. The problem is the 0. And we can see that from the graph. The problem is the 0. We have got the jump in the 0. We've got a discontinuity at 0. So what we're going to do is we're going to rewrite this as 2 integrals. So we'll integral of, from minus 1 to 1 of 1 over x squared dx. So we're going to separate it at the problematic value, at the value where this is undefined. So this is going to be the integral from minus 1 to 0 of 1 over x squared dx plus the integral from 0 to 1 over x squared dx. So essentially, if you just go back, if you think back to our graph, we've cut it in half. We're working out we're cutting it in half, working out this integral and this integral, but we're going to use it. But again, we still have the problems that we had before. This is undefined at this upper limit. This is undefined at this lower limit. So we still have to do exactly what we did before. We have to do limits. So this first, so this is equal to, and I'll write it underneath. So matches. So this is equal to the limit. I'm going to replace this 0 with an a. A tends to 0 minus 1 a 1 over x squared dx plus, now this time we're going to do, it was a separate one, and it's not necessarily, as this a is going to 0, this is whatever the limit variable I'm going to use here is not going to go at the same point. It's not going to be the same. So I'm not going to use a, I'm going to use a different letter. I'm going to use b. So limit, sorry, I apologize, I have limit as b tends to 0 of b to 1 over x squared dx. Now we just work out these definite integrals. We've actually already done this in the previous example, one of the previous examples. So limit as a tends to 0. This was, if I remember correctly, a minus 1 over x. So minus 1 over x, and we have to work out the definite integral of that between minus 1 and a. In fact, right now I put in extra brackets. I mean, these brackets, the reason why I didn't put these brackets in before, it makes it look more complicated. Plus limit as b tends to 0. Of course, let's integrate this. It's the same as integral before. It's minus 1 over x between b and 1. And now we're just going to work out what these are. So limit as a tends to 0. This, well, it's minus 1 over a minus, and when we plug in minus 1 into here, we get minus 1 divided by minus 1, which is positive 1, plus limit as b tends to 0 of minus 1 over 1, which is just minus 1, minus 1 over b, so that's just plus b, plus 1 over b. So we plugged in b here, and it's plus because there's a minus, because when we're doing different integrals, plug this in, then minus whatever we get when we plug this in. When we plug this in, you get minus 1 over b, so it's minus 1 over b. Now, so finally, we're almost done. We need to work these out. But notice this is as b goes to 0, as a goes to 0. Now, as a goes to 0, yeah, the minus 1 and this minus 1 here for the b tending to 0 are unaffected. But the problems are these values. As a tends to 0, this tends to infinity. In fact, it tends to negative infinity. And this 1 over b tends to infinity as well. Now, you may be tempted to say, well, this tends to negative infinity, this tends to positive infinity, so they cancel each other out. So the answer is just minus 2. But you can't do that, because this is a tending to 0, this is b tending to 0. For all you know, this a is much bigger than this b, or this b is much bigger than this a, we don't know how fast these are tending to 0 respectively. So this infinity and this infinity aren't necessarily the same value or same size. So we don't know anything from this. We've got infinities here, right? So this is getting infinitely negatives, infinitely positive. We can't say this is anything. So this is undefined. So this integral, not unlike before when we could say it tends to infinity, we can't even say that now. So this integral, question 2, doesn't exist. Okay, so that's it for integration from FP1. Go away, have a look at some exam questions. Make sure you shouldn't, so there's nothing really much new here. There's not in terms of content. The bits that you may really trip up on probably just the integration bit. So make sure you can do that from a course.